Thank you, everyone, and welcome to our Superpowering Innovation webinar. My name is AJ, and I'm really excited to be able to show off our acceleration station here at Diversified Plastics, powered by Carbon DLS. Over the course of this session, we will cover the immense capabilities of the Carbon DLS printing technology and how Diversified Plastics is a uniquely qualified production partner. Before we begin, there are a couple housekeeping things to go over. If you have any questions during this live event, please submit them in the Q&A at the bottom of the screen. We'll be answering some of the questions at the end of this presentation. We will also send the answers to the questions asked, as well as a recording of this webinar after the event. If you have any webinar platform issues, notify the host via your control panel. I think that's it. All right, let's get to it. Again, my name is AJ Frisell, and I'm a technical support engineer here at Diversified Plastics, specializing in our acceleration station additive manufacturing department. My contact information will be provided at the end of this presentation if you'd like to reach out for any more information or a sample made on these amazing machines. At this time, I would like to introduce my co-presenter and additive superhero, Jason Lopes. Jason is the former lead systems engineer for Legacy Effects, the first user of a carbon printer, and helped create many television and film blockbusters using additive manufacturing, including Thor, Avatar, Terminator Genesis and Salvation, 2012, Iron Man 1, 2, 3, Cowboys and Aliens, Real Steel, Life of Pi, Captain America 2, RoboCop, Pacific Rim, and many others. After leaving Legacy Effects, Lopes now helps companies leverage additive manufacturing. He's a strong advocate of additive manufacturing and has operated numerous additive manufacturing platforms to assist in the production of stunning visual effects and products. Jason was awarded the 3D Printing Industry's Maker of the Year in 2017 and the Dino Distinguished Innovative Operators Award in 2012 by the Additive Manufacturing Users Group. We're really excited to have Jason here with us today, but before we get to hear from him, I'm going to give you a brief overview of Diversified Plastics. Celebrating 44 years in business, DPI is a full-service contract manufacturer, proud to be employee-owned through an ESOP program. This really results in our employees being truly dedicated to the success of our company and its customers. Headquarters in Minneapolis, Minnesota, with another facility in Vista, California. Both of these locations offer geographic hubs for medical device and other industries. We have two facilities totaling 78,000 square feet. We have a Class 1000 clean room, as well as environmentally controlled work centers, including molding, assembling, and packaging areas. Both facilities are ISO 9001 certified, and additionally, the Minnesota facility is ISO 13485 and FDA certified. DPI delivers innovative solutions, and we are known for the highest quality products and exceptional service. DPI's team has the technical knowledge to build complex parts, including medical device, industrial products, defense, aerospace, electronics, and more. DPI offers custom close tolerance plastic injection molded components and assemblies, as well as carbon digital light synthesis additive manufacturing as part of our acceleration station that we'll be focusing on today. These core capabilities are backed with a full range of services, including design for manufacturing, validation services, prototyping, mold making, tool transfer, machining, assembly and packaging, and more. And without further ado, I'll pass it over to our main presenter, Jason.
Thank you, AJ, and thank you everyone for attending today's webinar. I really hope that the value that comes out of this really shows how we can enable you with what we call superhero technology, really being able to do things that additive hasn't been able to allow us to do up until now. I thought I would start this out today with playing to the theme a little bit and showing some of my previous work and what I've done with it, and actually where it held me back and where I emerged into the carbon universe for finding new solutions. So I'm going to take a trip back memory lane, and this was the first ever Iron Man Mark III suit that we did for the whole Marvel Iron Man franchise. And if you notice in these pictures here, these are the gauntlets, the hero gloves that are worn throughout the film that Robert wore. But one of the main things that we had a problem with was the materials and additive at the time. This is going back to around 2007 when we were in development on this, was there was just really no robust materials to be able to have prototyping parts get stronger in the downstream process. So we had to go to plating to bring out properties so we can actually use these in a direct manufacturing sense. And the reason why I chose to show these images today is because had I had carbon DLS technology back then, I think the whole way that we performed this movie and did this movie would have been entirely different. I would have been able to eliminate out a lot of my downstream processes for bringing strength back in and literally just go to a plating workflow, painting workflow, rather than a plating in between workflow. And I think that's essential to understand, being able to have materials that can hold up. And like I always like to show people, people think a movie like this is just a full-on digital movie, but the proof is in the pudding. This is actually Robert on his first day of being fitted in the helmet. And this is actually his stunt double wearing the full-on suit that was actually prototyped in SLA and then cast and molded into different materials. But since there, I was still having problems being able to go direct manufacturing with the existing market. This is a movie, Real Steel, and we did all of these high-performance robots that were hydraulically controlled, as well as RC controlled, and a lot of times parts were breaking on set. And at this point, this is when I had first met Carbon. It was a little too late in the pudding to revisit this project to be able to enable what we were trying to accomplish. However, I quickly moved forward from there, utilizing Carbon every turn that I could. This next slide here is a perfect example. One of the tasks that I had was, we did a lot of animal reproductions on sets. And one of my tasks was, how can we eliminate and automate a puppeteer on, let's say, a tail? This was a pretty cool study that was literally done in one day. And I'm going to play the video, and you'll see I'm able to take an engineering rigid material and look at it in a completely different sense through design, and actually get more of an elastomeric property out of a rigid material. This is how I really say that Carbon technology can bring out these superhero powers, because it allows you to explore areas of design to bring out things that were just not possible in any other way. So I evolved what you just saw in that video to more of an automated process from there on version 2, where we eliminated even more plastic and automated it fully. And we'll hit play on here. And as you can see, I've gone from that previous video where there was a lot of plastic being used from the printing process to eliminate it even more, to get stronger, lighter, and accompany it with metal parts as well. This was game-changing for us. And finally, I had a technology that I really felt like I could engage with. And I think that's the big piece of the puzzle here. It's one thing to output something and have a part in your hand, but it's another thing to really engage with that technology all through the process, upfront in development, so you could learn the ins and outs of it, see near real time how things are behaving in the print, and really incorporate that into your workflow of designer and engineering. I think any designer, any mechanical engineer can really appreciate the way that you can engage in these technologies to just make a better product at the end of the day. And then in this next example, this was from a movie that I had worked on for a really long time for Guillermo del Toro, called Shape of Water. And you'll see in the first couple of pictures some clear materials, but that bottom picture is what we would call a maquette. This is actually a puppeteered maquette. You can see the gentleman holding the rod that holds onto it. So we basically have a rod on each side, and we can actually puppeteer and move this this maquette at small scale before we decide to go full scale. But where the enablement is here is being able to create something at about 22 inches tall in a matter of like less than 2 days, and then take all of that time that we saved up front to apply it in other areas downstream is so invaluable to any product development process. And I know these are movie items that we're looking at, but I want you to think about them in relationship to the whole workflow of getting something locked into market. When we can shave time in any area up front to dedicate more time to another process, any type of labor, we're gonna win in that area using additive. And here's a great example here of being able to shave all that upfront development time to really focus on a downstream process of something very individual and unique. And here it is in a paint scheme. You'll notice here the lights will turn off in a couple seconds and a black light is introduced. We were able to really exploit a lot of techniques that we learned on Avatar and started creating ways to downstream paint and animate color and light within that paint. If we didn't have all of that upfront development time shaved in design and 3D printing, we probably would never be able to exploit and find techniques like this. So it's pretty exciting just on the acceleration. And I really love, today you're going to learn about the acceleration station. And there's no better technology to put inside a diversified acceleration station than carbon technology for this very purpose. Here's another great way of thinking outside of the box. Makeup artists. Makeup artists are probably the furthest thing technically from additive manufacturing and 3D printing. However, when you show them what can be done in a traditional process and how you yourself can innovate in something that hasn't changed in many years, and we're not trying to switch over the way the artist created, we are trying to show new ways of using a tool to get to a better result. And I think that's the key. So here's an example was for Guardians of the Galaxy 2, where I took a clear elastomeric material and actually incorporated that with a very high-end makeup artist. And it's a biocompatible material, so we can actually do a lot of these makeup appliances with a new way of utilizing 3D-driven design to drive this market. You know, I was used to, at the time, any artist really putting up their guard and trying to block out technology. But once you really show this is not about the technology taking over, this is about the technology aiding you into doing these impossible tasks that you're given to bring to market, use it as a tool, just like that toolbox in your garage, and see how it can aid and get you to market faster, no matter what type of market that is. And then here's the last example that I wanted to show. And I actually, if you could see me on video, I actually have this part here still. This was an early exploration for a Captain America chest. The first thing you'll notice in the top left-hand picture is that that chest is probably over 10 times the size of a build platform, at least. So it requires different ways of thinking. How can I print something bigger than the constraint that I'm giving of said technology on its limiting size? Well, as you see here in the other three pictures, we actually produced these parts that were bigger than the platform, but how do we do it? Well, playing to the technology and understanding how the technology works, which is what I'll show you a little later on today, is carbon's a two-step process. We know we print in step one, and we bring out the mechanical properties in an oven in step two. So in software, I took these ones and zeros and actually rolled them up like a fruit roll-up in software and created cylinders. And we printed cylinders of this material, this elastomeric material, super fast. And after the print finished, we put it on a high temperature buck, went into the oven, and then formed it in the oven and brought out all the material properties. This is a part that you cannot mold. It has a lot of overhangs, like the crest of a bird on a chest. So impossible geometry, but utilizing how the technology works and the steps involved got us to do an impossible object, and something that even the OEM at the time said wasn't possible due to the size, but we just looked at it a little differently, exploited the technology for how it works, and actually brought this to market, and as you can see, fabricated it together for the suit. I think that's pretty exciting, and this is what I really like about carbon technology. It allows you to approach things from a much different way than you have before, and really open up the boundaries of what can be done. So up at Carbon, we have the phrase 3D as it's meant to be, and we really like to show, like, this is not just talk. These 5 verticals that you see on the bottom of the screen, automotive, consumer, dental, industrial, and life sciences, we actually have parts all the way out in production, end-use parts at high quantity, high volume in these examples, and we have case studies behind it to show it. In the automotive vertical, companies like Ford and Aptiv are using our rigid polyurethanes and our epoxy resins every day to do PPAP productions and actually have parts on cars. In the consumer world, everyone knows this for our Adidas sneakers, but more recently we brought the specialized bike seats to market, as well as CCM hockey helmets too, and Rydell football helmets. In the dental space, dental has always been big in additive manufacturing. However, we've kind of flipped the script on that. In the thermoforming application, for example, we can now reclaim resin and reuse resin to get more efficiency and economics for all patient data. And we've also have a solvent-free downstream workflow where we can clean parts, eliminating solvents in this application. In the industrial space, we actually have parts that have went up to space. In life sciences, more recently, during the COVID-19 pandemic, we brought to market nasopherical swabs using a third-party dental material and actually have them out commercially available now. Up at Carbon, the platform for DLS, and DLS is an acronym for our process, which means digital light synthesis. We kind of operate in three buckets up at the company. And the first bucket is hardware. And I always refer to our printer and the hardware as what Elon Musk has done for the vehicle. No different than what Joe DeSimone has done here. He's taken a printer, which normally is a standalone island in a facility, and really connected it over the air back to Carbon, so we can have maximum uptime. We can monitor all health and diagnostics of the machine and actually have the software tune the hardware for preventative maintenance when needed. The day that you get a printer is probably its least performing day. Every day from there, with our over-the-air software updates and our algorithms, the printer and print planner just get better and better as the days go on. Our software, it's one thing to control the hardware with software. It's another thing for user experience. The front end of our print software makes things super, super easy. And that print button that you hit to send your job in and begin to build actually is so complex on the back end, running FEA simulations of our process to guarantee that you get out a first print success in the best possible manner. And then we've even enabled software further, where we now have a texturing module inside of it, as well as a lattice design engine. And we'll learn about those a little bit later. And then lastly, materials. Because of our process, we can really open up the chemistries and use materials like you've never seen before. I often say that Carbon is more of a material company than it actually is a 3D printing company. And this is what's great about having each one of these buckets under one roof, is a company like Diversified, being our partner, gets direct access to all of these experts at any time. So if you have a complicated program or questions on material compatibility and testing, we can enable those conversations immediately and get you the answers that you need. So now I'd like to talk about, Diversified and the acceleration station in the bucket that they sit in with Carbon, and that's our carbon production network. We've always felt up at Carbon that ourselves do not want to be a printing bureau. So we've created the carbon production network to be extensions and experts of ourselves. So Diversified is a certified production partner. They carry ISO 9001 and ISO 13485 certifications. And this is where it gets a little bit emotional for me. In full disclosure, I only met Diversified after they came on board at Carbon. And any company that enters our network, I always do a lot of research on, and I want to learn who they are. And the first thing that really impressed me is the whole idea of the acceleration station and being able to complement traditional manufacturing, injection molding, you name it. And looking outside in, I immediately saw that they shared the same view that I did, and that's how can additive complement, the traditional process and actually bring products to life and help in the process, in the workflow, whether it be a bridge gap, prototyping to product development, or low volume, medium volume, even up to serial production with this technology. And that's the first thing that I noticed, is really Diversified was thinking about this a lot differently than other people do. A lot of people think that, oh, this is now a new tool and we're just going to try to use this tool all the time. But it's much bigger than that. It's how does it fit in the whole overall picture? Secondly, if you've ever been up to Diversified, anyone attending today's webinar, it's all about the people for me. And the minute you walk into the facility, see all the equipment that they have and how they operate, it really just marries that technology to the human aspect perfectly. And, working on any project together is absolutely amazing. The team is so talented up there on what they can do. And just like the name, Acceleration Station, I've seen acceleration between all of their operators and all of their staff members adopting additive into the workflow on how can it complement and help make a better product. So I really, really enjoy working with Diversified as much as possible. So now we're going to give you a little bit of an overview on how the technology works, and then we'll have a little special treat after this slide that I think people will appreciate. So I'm going to hit play on this video, and the first thing that you're going to notice is the build platform lowering into the window cassette. This is probably the only commonality between Carbon and another process. The next thing that you're going to notice here is a movie play. This is a black and white movie, what's called an alpha channel movie. And our projector actually shoots up through this video on the white and actually solidifies the part that's being built. Now, if you pay attention to that part, you will see it's consistently going up. It is not going up and down at all. So we can build a continuous process. And after the specials treat, I will show you a little deeper how this process works and what it enables. So we'll see the part come up right now. And as soon as she breaks the seal and raises out, this part is now ready for step 2. But rather than going to step 2 first, I thought we would do a special treat. And I'm actually going to cut to AJ live in the lab so we can show you how this process gets initiated.
I'd like to welcome everyone to a live look inside the acceleration station here at Diversified Plastics. We're going to give you a brief demo of what it takes to start a print in a Carbon M2 printer. So right now, Clayton is adding the cassette to the printer. It's already been pre-dispensed with all the resin that we need for this print, and we've already added the print file through the user UI, if you can see in the screen down below. So the next step is to add the platform. This platform actually has a smart chip tracking system that allows us to track every step of the print process, starting from the print all the way through the wash, which is really great for user traceability. So now I think we're gonna adjust this platform here briefly and start the print. So we just really wanted to show you how easy it is to get a print started on the Carbon DLS system, and how the smart tracking really allows us to know what's going on every step of the process.
So what's going on now inside of that print that we see live on the screen is our part is in the middle, as we see in this video. We have added contrasting agents so you can see the resin flowing on the left to right down into our dead zone. Our dead zone is what makes this process possible, and it solidifies into the part. And you'll see, once again, there's no up and down. It's a continual Z motion. That allows us to have fully dense parts that are isotropic, and it really opens up new chemistries that can be used. So after this print is finished in an engineering material, it's actually a 2-step process to bring out all of those material properties, something that we call 2-stage curing. An engineering material like carbon is called dual cure material. So in step 1, we actually set the shape with light. The UV light will bring a part into green state and the full form is there. However, the mechanical properties are not of chosen material. If you were to drop it, it'll break. If it's an elastomer, it can rip easily. But after we clean that print, we then go into our convection oven for anywhere from 4 to 8 to 12 hours, depending on the material chosen. And that's where the polymers will cross-link and bring out full material properties. This is also the process that I exploited for my superhero power, as we saw earlier, for printing within a limited constraint and utilizing that second stage to be able to open up and do new things. Some advanced things that we can do in this 2-step process as well is what I call DLS over curing, where we can bond 2 different materials together in the oven and have the polymers cross-link through both materials family, forming that cohesive bond for us, eliminating the need for adhesives, etc. If you're interested to see like what can I do with multiple materials in an advanced state, please reach out to Diversified and we'd be happy to talk and go really deep in an advanced way of what can be enabled in this process. So a little bit more of a close-up of an actual part, like we'll see that comes out of the acceleration station today. If you look on the left-hand side where conventional 3D printing, orientation matters. How you orientate will only give you the best result in one direction for strength. Anywhere else you orientate will produce a weaker part. And if you look at the first image of the 400 micron close-up, you'll actually see those layer lines inside of the part. Those are actually weak spots in the part that could give you a susceptible part failure out in the field. Well, if you look at digital light synthesis, we've taken orientation really out of the equation. X, Y, and Z will give you full properties. And if you look at one of our parts under a 400 micron scope as well, you'll see the isotropic properties right there. It has a grain structure very similar to an injection molded part. So once again, if you look at us compared to a powder-based technology under 2x magnification, you can actually see the porosity inside of the part. In the digital light synthesis part, you can actually see the isotropic properties. This is very important, especially in medical life sciences, when you need to take these materials maybe to a sterilization method or anything else, and you don't want any uptake of moisture or condensation, anything like that. Fully dense parts is what you get out of our process. So where does Carbon DLS sit with everything else that's out there on the market? Well, if you look at the left-hand side, we have our heat-based technologies like FDM and SLS, but their surface finish isn't as good to the eye. They can be porous parts. The level of detail just isn't there, and there's limited material options. On the right-hand side, we have the exact opposite of the equation in Polyjet and SLA. These are high-resolution, great-looking parts. However, they're not stable in UV, and mechanical properties are a lot weaker, more of a prototyping material, and they have limited material options. In a lot of cases, especially on the Polyjet side, if you were to drop a part, it will shatter right in front of you. Well, DLS takes the best of those worlds and brings them together in one platform called digital light synthesis. So we have high performance materials with excellent surface finish. We can produce fully dense parts, high detail parts, UV stable parts, and we have a wide range of materials with more coming to market all along our roadmap. So a high level overview of all of our materials that are available through Diversified. We have our EPX82 material that's very popular in the automotive and the industrial market. We actually have parts on cars. This image on this slide of that fuel cap, that's actually from the Lamborghini Ursa. Once again, this is an epoxy-based material. Our next material, FPU50, it's one of my favorite materials actually, and I have a slide that I'll show you later, is flexible polyurethane. Think of living hinges, caps and closures. Our next material is CE221, cyanate ester. This is our high temperature material. Geometries after bake can withstand about 230 degrees Celsius. Our next material is our flagship material, RPU70, rigid polyurethane. Think of an ABS-like material. Silicone 30, SIL 30. It's not a true silicone, it's a silicone urethane. It's biocompatible. It's used for a lot of soft touch and padding. This example in the picture is for a pair of latticed out earphone cushions. Probably what we're most known for are the next two materials are elastomerics, EPU41 and EPU40. Two opposite ends of the spectrum. EPU41, think of the Adidas sneakers for energy return. EPU40, think of impact absorption, the Rydell football helmets, or even the specialized bike seat. However, programming and designing through Lattice, you can actually alter those base properties and variably control properties throughout your design space inside of them. Our next material is a dental material, DPR10. This has been fine-tuned for speed and accuracy in thermoforming applications. And then another very big material that's just gaining day-over-day usage for production applications is our MPU100, multi-purpose polyurethane. This material is actually on file at the FDA as a material. It's Class 6 certified. It's a medical grade ABS. And then one of our newer materials, the last one on this slide, is RPU130. Think of this in the consumer world, industrial world, and automotive world. It's like an ABS with flex with a higher heat deflection. And if you'd like any data on any of these materials that I've just mentioned, please reach out to Diversified and we can supply all the TDSs, etc. So one of our newest materials that's actually really exciting for me is it's not an engineering material and it's not a material from carbon. This is LOCTITE 3ND, IND 405 Clear. It's actually through a third-party partnership with Henkel. This is our first foray into a single cure clear material. It's a semi-rigid, high elongation at break, best-in-class toughness, and it's, like I said, it's a one-part resin for a simple workflow. Like I had explained earlier, the oven step to bring out the engineering materials properties, you do not need the oven in a single cure material workflow on carbon. The workflow is print, clean, and go into UV cure rather than convection cure for 2 to 5 minutes per side, and your part is ready to go out the window. Now, the one really nice thing about this material is, just like what additive is known in the SLA world for clear materials for a long time, is you can really clear out this material nicely and easily. This example here was actually done with just rattle can clear. So not even automotive clear. It's an off-the-shelf Krylon to just show for these examples. You can also pre-print tint this material and actually tint it in certain colors if you'd like. And working with it is really nice compared to the competition's clear materials. The surface hardness on this is higher, which allows me to more efficiently and quicker sand and prep the surface of this material for any downstream workflow. And then one of the last materials that I'll talk about is what's coming to market over the next month or so. It's a cousin of our epoxy material, EPX86FR, for V0 compatibility. So this will be our first material that will be hitting the V0 spec. I've actually done some low volume productions early on with this material. It passed its vertical burn testing for the client and actually did very low volume production on 3 different part IDs in this material. If anyone on this webinar today is interested in this material, Diversified does have access to this material through us up at Carbon, so we can always run samples and benchmarks if you'd like to see this material and put it through the test yourself. I think this material will be commercially available most likely at the start of May. Always check back with Diversified for updates. As we know, delivering roadmap items during a pandemic is a little challenging, but up at Carbon, we've done actually pretty well with that in the pandemic. So all of our materials are compatible with multiple sterilization methods. I won't bore you and read through everything on this slide. However, everything here, you can see we have all of our materials which pass, and I would say basically all forms of sterilization, excluding at the moment autoclave. We will see more things on our roadmap that have to do with being able to survive autoclave sterilization. They're currently in development. And same thing with biocompatibility. We've tested for 3 forms of biocompatibility. And you'll see at any time, if you want to request this data, we can get that into your hands so you can see if our materials will work for your programs or applications. This is one of the really nice things that I think sets Carbon a lot different than competition. The fact that our materials are certified on Prospector is a really big deal, at least for me, and I know a lot of our customers. Having it listed with reputable other materials that people are using every day in traditional manufacturing is just second to none, and it shows you Carbon's commitment with not only just making prototype and fit form, but the true mission of adoption into volume production with additive manufacturing. Once again, you can find all these materials on Prospector, but if you would love more information or even request a deep dive meeting with our material scientists, please don't hesitate to reach out to Diversified. They can pull all of it together and we can go really, really deep for your needs. So this is what I consider one of the biggest superhero powers of this technology, is agile manufacturing. If you look at a traditional workflow between design, prototyping, locking at tooling, and then spitting out for end use parts, we really, the product can suffer to a degree within that timeline workflow, as well as economics. So if you look at agile manufacturing, we can eliminate all of that tooling. We know numbers can be high, numbers can be nominal in tooling. However, we can eliminate that. We have minimal lead time. We can really go through iterations and revisions all along to make a better product, even in prototyping scenario before we get to production. It's very common for even myself when I'm doing something for a client or for an account, I'll have one revision on a platform set up, but also 2 other revisions as well. As we add to the platform, as long as we stay in that same Z height, and if we're working with the same product or assembly or part of the assembly, I know that any revision I'm going to add to that platform is not going to add time to my build. So for a designer and engineer, that's where this unleashes. You can really test the waters by showing multiple options at once very fast, get them in hands, get client feedback, make some tweaks, finalize those tweaks, get them back onto the platform, get them back in hands, and get that decision made and then move into production optimization for volume scale. So really being able to shave all of that upfront lead time off just makes a better product at the end of the day, that we don't have to work within a constraint necessarily, and we can devote all design changes and all of that tooling dollar to the development process even more and just lock for production. And here's an example here, minus the customer logo, obviously. But if you look at a traditional approach for a PPAP application, generically speaking, it's an 88-week timeline getting there. Well, the same customer actually brought something to market in the automotive space with Carbon DLS technology. And as you can see, we shaved off about 50% of that time. That is huge, especially upfront in design and material testing, meaning we technically never have a lock until we say we have a lock. We're not constrained. And proof is in the pudding. I would love for you guys to visit and look at as many case studies as you can on the Carbon website, and Diversified has case studies as well that really show this time to market and how we can really aid in bringing these products even better and faster. And at the end of the day, for me, it's about adoption. The more that we can show real world case studies, I think the more it's going to lean into more people adopting and more companies wanting to be educated and taking their first step into this journey. It takes a lot for a company to reinvest how they do things, to look at additive manufacturing and 3D printing differently. And this is where Diversified comes in and can really help. They will educate you. They will help do discovery and show you what makes sense, how to look at things differently. It's one thing to see 3D printing and additive manufacturing from a marketing landscape, but it's another thing when you work with a partner like Diversified and they can really show you and give you those aha moments on any level of production or program to show you how to get there faster and adopt this to complement. Here's another example that actually came out of the pandemic, and this really leads into what I was just saying for adoption. This was a time of need for COVID-19. This is an eyewear frame for PPE. Rather than a full face shield, it's an eye shield. And the original product was injection molded, but everyone's complaint was that they just sat loose on everyone on a generic head. They didn't have a tight fit. So utilizing additive, we actually redesigned the part and printed out about 100 a day for a quantity of 1,000. It later grew to 2,000, but we satisfied two different things here. We satisfied the time of need for urgency. We had it in their hands daily, dropping off parts. But we also were able to get a better fit through design with additive. We added customization, actually, since these were such a time of need and limited until the injection molding tool was ready. We actually customized with the employee names on the side frame, since they were responsible for these for one shift. So we got to play with bespokeness in this. The minute we got the thumbs up, we started locking the tool. The minute the tool was locked, we just shut off this bridge. The first thing you'll notice that cost, that these are about $5.50. We're never going to match injection molding cost. However, that 10 days of not having a tool and not having product in hand, this is where additive really shines. This opened up inside of the hospital network all the executives to take a bigger look at additive and have discovery sessions and meetings with us to really go deep to see what other projects can we look at to bring additive into. Even if it's a bridge gap, or even if it's a old replacement part that they couldn't source anymore, could we convert it over to additive and get parts in hand and really start adopting it more in this workflow? So a little bit of like what's really good for a system. I think it's really important to know just like the tools in your toolbox. What's this screwdriver for? What's this tool best for? And same thing goes with additive manufacturing. So some of the sweet spots for digital light synthesis at Carbon is first and foremost part consolidation. The top right-hand corner is a great example. You know, we go from 3 parts, 8 screws, and 2 O-ring seals, and a tooling cost down to a single part design. We're now eliminating having to source items. We're eliminating that human hand assembly costs, dropping economics down, but more importantly, making a better part at the end of the day, pushing it where traditional leaves off and might hold back the performance of a design. we can exploit that through the new principles and philosophies of designing for additive, specifically digital light synthesis. Small parts do very, very well in our technology. It's not that we can't do big parts. Small parts are great for throughput and volume. Textures and lattices are amazing on our technology, and the offering I'll show you in a couple slides from now. You can apply texturing just like a Mold-Tec call-out. Or if you want a performance feature from a lattice design, we can enable that through too at the acceleration station with Diversified. They have access to all of these tools and features. We do fine features very well. By default, we print at 100 microns. We can print at 50 microns as well as 25 microns. Cosmetic surfaces, as you see in the pictures, very close to a Class A surface finish. And with our high temperature material, cyanide ester, we can take air and water up to 230 degrees Celsius. So some of the values that we bring in design strengths is we can really open up impossible designs and better performance through latticing and texturing. And couple that with customization, and you have a production that just can't be done traditionally. And if you look at us versus other additive technologies, we have really our approach to engineering grade materials is second to none. These are two-part urethanes and epoxies that you just can't do in other systems. You can go from prototyping to production in just one process. So what you're beta testing in your hand, that is your end use material once we lock for production. And we do embossed engraved text very well. Logos we can customize into our texture tool, as well as threads and cosmetic surfaces. So a little bit into our digital texturing. What's really nice about this approach, if you talk to anyone that's been 3D printing for a very long time and they show you a part in hand and you say, oh, it would be great to add a texture to this, their eyes will probably roll because normally textures are an afterthought in 3D printing, which means that up until carbon came along, you had to go back to your CAD, bring it into some type of application that can help you texture, need processing power, watch paint dry because it takes so long, output it, and then have your client tell you they want to see a change, taking hours and days to deliver that. Well, up at Carbon, we solved that by when you load in your final geometry to print, all AJ at the acceleration station has to do is enter the texture module, click on a surface, adjust that spread of how much wants to be textured, and then apply one of our textures. That easy. It processes in under 11 minutes most times through Amazon Web Services. So once again, you don't need that local processing power. And we can really apply neat things here. We can do noises, leathers, geometric patterns. We can go positive, negative, and we treat it just as you would texturize a tool. If we're going to add to it, we're going to add to the surface. If we're going to take away from it, we're going to cut into the surface. Now, you can even come forward with a Mold-Tec call-out, and we can match that through our software. So something to really consider and think about. Also, the really neat thing here is once we texturize, you're not just locked to the carbon process. So you can actually, with Diversified, texturize something and use it for another process if you wanted to and output it. Another really nice thing that AJ's got some access to over there, and I can't wait to see what he does with it more and more, is he's got the same design engine that we do up at Carbon. We take populating a solid design space very, very easy. And if you look in this screenshot here, this is the actual software. You bring in a solid design space, choose your material, and then you can start altering the struts and the cells to get different properties and see them plot out on the graph. If you like what you see, you can just hit the apply button, and within about 8 minutes, you will have a textured design space come back that you can send right over to the printer and have your first elastomeric lattice out. Now, you could also use this for rigid materials to lightweight out parts and keep them strong as well. The possibilities are endless, and I know everyone wants to talk lattices. However, most people don't realize how difficult it is to do. So anyone on this call really wants to start experimenting and seeing lattices very quickly, reach out to Diversified. They will take you through the journey and show you how this is done very easily. It's funny, yesterday alone, within 33-minute time period, I kicked out 8 different lattices for one of my projects with the push of a button. Super easy, super fast and efficient, and that's what we're trying to bring to the masses. We're trying to take something that's been historically very complex and engage with you in a new way to show you that it doesn't need to be as complex. We can work on the complexity on the back end and have fun on the front end. So I had mentioned earlier small parts, and this is what I call the sweet spot for anyone that's really trying to understand economics behind this technology. I mentioned earlier that we will never match injection molding quality, cost price, I should say. However, if you look at smaller scale items, we can push the bounds a lot differently. We can do higher volumes, and also smaller scale tends to not, in our process, not have to have the usual suspects for supporting and overhangs with angles, etc. So it's really a nice entry point into understanding DLS and get a grasp on the economics behind it. Here are some examples of breaking the boundaries too that I'd like to show. You know, on the left, this is user-specific data for custom product development, right? We have algorithmic design for latticing on the shoes. For the Rydell football helmets, we actually scan. It's a whole scan to design to print workflow for the football helmets in Rydell. And if you look at lightweight and comforting in the middle, BD, I have a slide on this I'll go a little deeper on. They took an injection molded part ID, converted it over to DLS, and are actually in digital DLS production with this part now over time. Vitamix nozzle that you see on the bottom, this is another great example of taking part consolidation into effect, having an FEA-driven design to give a better performing product, eliminate it down to one part, and just have the economics, and it outcycled its injection molding counterpart with a 1.5 million cycles in the field. And then the last bucket, inventory on demand, which is very exciting to me. Why store inventory anymore? You can get feedback from the field, incorporate it into a new revision, output that, and have that be your on-delivery master now. So anyone that calls in for a replacement part, you can just print it on demand. And then the Ford Raptor plug here is an actual production application part. You'll see texturizing in there, their logo, as well as serialization for full traceability through the manufacturing process. So up at Carbon in life sciences, we're really accelerating medical device design and manufacturing. Like I had just shown you in equipment components is a very big win. Single-use instruments, one and dones, especially with our multi-purpose polyurethane, are second to none. This material, like I said, is on file at the FDA, so you could bring your product up through for FDA validation alongside with this material. Non-surgical devices, you know, in orthotics, hearing aids, etc. The scan to design to print workflow is just enabled even more in our process. It's very engaging, it's very welcoming to a design engineer, but more importantly, to the end user / customer. We can now really bring in fit and comfort into a different way into a lot of these medical applications that you just couldn't do before Carbon. And this is that slide that I wanted to show you earlier. This is our flexible polyurethane. And this is, if I had one wish out there in the industry, it's that people would push living hinges even further along. This is an example that I did about 2 years ago now. It cycled about 250 cycles, and it also had a snap fit that held 22 PSI for a shampoo cap. I'll hit play on the video so you can see, and you should even be able to hear the snap fit when it happens as well. But we can finally develop and produce real-world products that outcycle and hold up just like injection molding has for years for the industry. We can now start bringing products like this to market through these materials. We'll get into some case studies here, especially on the automotive side. This is really neat. It's one thing to say you have parts on cars, but it's another thing where you didn't have to sacrifice to get the part on car. So on these three examples here from Ford, you'll see serialization, you'll see texturizing. Like I said, serialization is really the point that I want to hone here on, is that Carbon came out of the gate with production mentality on their minds for our process. So all of our software up front is really built upon having that traceability to go fully downstream in any production process. So we have a very robust serialization tool right at the printer level. We can use tokens from the printer that go back inside of the dynamics of what's happening for the project, or even customize labeling as well. And it will append up as the production goes on and you queue up for your volume production. You can revisit it years later and it would still append serialization and continue through the production. Here's another example that came out during COVID-19. I think the real thing to hone in on here is for this microfluidic diagnostic devices, it was just weeks to market. I think it was a total of 5 weeks to get it fully out into market utilizing RPU 70. And especially as we're going through a pandemic when we have supply chains that have been compromised, think of this just for any one of your projects, how quickly you can get something out there, just even into a testing environment. Haven't been able to do this before. So what I really, really like about the whole additive mission as a whole is we're going to see better products being enabled. No sacrificing have to be made. And this is, once again, a great example. This is not a small part by any means. So being able to rapidly go through 10 designs over 4 24-hour design, test, and print cycles is second to none. And here's the cassette adapter. This is one of my favorite slides, and it's such a simple slide. This is a traditional one-to-one conversion that was injection molded. They were originally squares on the back for lightweighting. However, if that design wasn't modified, every one of the squares would have had to been supported, which meant labor touch, as well as wasted support material driving economics. Operator asked a simple question, can I clock it 45 degrees, make them self-supporting? Able to now drop economics by 11% on this overall cost per part. So a really big win there by looking at it for an additive design philosophy rather than traditional manufacturing. Another one here too, a 70% cost savings for low volume production. These radioactivity sensors, upgraded designs and introduced them to the market to the same year. Traditional manufacturing with injection molding, it's just cost prohibitive. So being able to rapidly design and innovate like that will show you how we can drop down economics while bringing very rapid development to market. And then this is the one that I had touched on earlier, which is the Agrifac spray nozzle. This is all being converted from traditional. These are for nozzles out in the field for farmers. As they break down, they call in for replacement nozzle. So now we can take all of that feedback from the field, incorporate it into a new design, print it on demand. If it performed better, that becomes the newer shipping rev. So now we have 2,000 units a year and decreasing over time due to constantly being able to up rev design through a production on demand deliverable process. And now for this next case study, I'm going to throw it back to AJ.
Awesome, thank you, Jason. Here I am in the acceleration station, but yeah, I'm gonna do an abbreviated version of this case study. We really wanted to touch on it for its current implications in the world. Thaddeus Medical Systems reached out to us looking for padding that minimized shock and vibration for their cold chain vaccine and medical specimen transportation case. So roughly, it's a Pelican case that allows everything to be held at the proper temperature. But when utilizing SIL 30 in a gyroid lattice structure, we're actually able to minimize shock and 3 different types of frequencies of vibration. So, yeah, next slide, thank you. So the problem that this is solving is usually the damage and loss rate for shipping medical supplies is around 20%, which adds up to a $35 billion yearly cost, which leads to a lot of negative implications. And so Thaddeus is really solving that by adding the durability and the extreme ability to travel anywhere in the world, and also Bluetooth tracking and supply chain management. So in the development of this gyroid lattice, Thaddeus reached out to us and we went through a couple different iterations. We found that EPU 40 and SIL 30 hit a couple different characteristics that we needed, but most importantly, the SIL 30 was the one that was able to minimize all the different types of that frequency. So we like to say Diversified Plastics was the only place that was able to produce this and print these effectively, and this case is currently in beta testing with eyes on being released here at the end of the year. Awesome. So I'm going to skip cameras now, and we're going to go back to the lab and check on that print that is printing. So here we have this print that we started a little bit earlier. You can see now that it's leveling up off the platform. We did print another one just in case we went a little bit quick, which I believe we did. So I'm going to move over here. And this is the finished version. This is a lattice structure of our DPI load. So here we'll have Clayton take this off. And so at this point, we would remove all the supports, wash this part with solvent, and move to a UV cure. That's because this UMA material is a UV curing material. We normally have parts enter the smart part washer or go into an oven to be able to set up molecularly and finish the print off. But yeah, we really just wanted to get eyes inside the acceleration station because as you can see, this is a state-of-the-art lab that we have here, modeled after Carbon's actual lab. We have 3 Carbon M2 printers and 2 Carbon smart part washers with 1 dedicated for medical. So that is really what we have for you guys today. Like I said, we're really happy to have everybody here and show off the capabilities of our lab. So now I'm going to kick over.
AJ, one thing that I just wanted to point out that you just said, if I may ask, so you are actually, with your 2 different smart part washers, you actually have 1 dedicated just for medical material?
Yes, that's correct.
So that's really good to everyone listening. So in being 13485 and really understanding the mission for production in medical, just eliminating that cross-contamination possibility by having 1 dedicated washing station just for the multi-purpose polyurethane medical grade ABS is second to none. And you really don't hear of this too often, which really shows you the acceleration station. It has that production mindset for medical first and foremost on their backbone. And I think that's really important to note.
Yes, of course. You know, a lot of things that we went over today are, really show how Carbon excels at prototyping and innovation. But what we're really focused on here is being able to lead projects through that whole process and then end in a production mindset with our full validation and our, the backup of our large injection molding business. So that's something that we feel that we really excel at.
Great.
Awesome. So I'd like to open it up to a little bit of Q&A here. I know we only have 2 more minutes in the time slot, but let's see what we have.
Great. So one question we have is, can you explain a little bit more about the stage 2 and what cleaning entails?
Great. So I'll start at AJ, and then you can back up after me if you'd like. So after we print, we have to now clean wet resin off of the material that didn't cure onto the part. So up at the acceleration station, as you saw, they have the smart part washer. You put the platform of the parts into the cleaning station. It will lower into solvent and clean within 6 to 7 minutes automatically, and also add traceability for the production work stream as well. This is important to get all that wet resin off. So this way now, when we go into convection oven in step 2, we heat at about 120 degrees Celsius to cross-link the polymers and bring out the full material properties. As soon as the oven bake is finished and it cools off, the parts can be touched by hands and go out to customers.
Yeah, Jason, you knocked that out of the park. Yep, we have multiple different solvents for different materials. That gets into the nitty-gritty.
Great. And I think we have time for one more. And we have a question about stage 2 curing without adhesives. And are you able to combine different materials?
That's a great question. So this advanced bonding of materials, I would not say this is for high volume production at all. This is more for fit form, getting an idea of a final assembly product. But yeah, we can take a rigid material and an elastomeric material, print them individually, clean them, combine them together after the cleaning, and then go into that oven at 120 C, and then we should cross-link between both material families, forming a cohesive bond. we used to have a great example in our sales kit that we sent out of a bicycle grip, actually, that had a rigid inside sleeve with an elastomeric lattice on the outside. If you've ever seen that geometry from Carbon, that's actually been done in this process inside of the oven.
Great. And then the rest of the questions we can follow up and answer in our email.
Okay. So I would like to thank everyone today. First and foremost, I'd like to thank the whole crew at Diversified. Working with them is great. I've been working with AJ for a couple months now, and seeing his acceleration of learning additive and the Carbon process is second to none. Soon I'll get to sit back and watch him host these kind of webinars as he becomes the full-on expert. But you're in really great hands with the team at Diversified. I really encourage you to reach out and work directly with them. Have fun working with them. It is a lot of fun, and see what magic we can all produce together.
Yeah, thank you, Jason. I'd like to follow up. Thank you for your time today. And it's really special hearing your background as it applies to this material, because you really are a superhero and an expert in everything here. So yeah, I'd like to thank everybody for coming. And like we said, we'll reach out with an email at the end of this. This webinar will end, and you will be led to a form that has more contact information and the ability to request a sample from any one of us. So thank you.
Thank you, everybody.